Okay. I'm glad to be here to present to you some results on the inclined geosynchronous orbits. Here is the outline of my talk. A very brief background followed by theoretical analysis, numerical results, a possible mitigation strategy, and a summary. First of all, I'd like to talk about why we did this research. This slide shows one of the reasons. As you may know, 5 inclined geosynchronous orbits are now in space. They belong to Chinese navigation system, and they be called IGSO. The table 1 shows part of orbit elements of these IGO satellites. Comparison with conventional GEO satellites, they have a very high orbit inclination with around 55 degrees. It seems IGSO is a kind of special orbits and different from a conventional GEO. So what will happen for these IGO satellites after a long-term dynamic evolution? That's one question we want to answer. Another reason comes from IDC mitigation guidelines. For conventional GEO satellite, IDC has defined a protection region like this, region D, that recommended that all spacecraft in GEO should be maneuvered to dispose orbits sufficiently high at the end of mission. Let's say about GEO altitude plus 200 kilometers. So the question is whether this recommendation is also feasible for these IGO satellites after the end of mission. That's another question we want to answer. So now let me try to answer these 2 questions. We start with theoretical analysis. For conventional GEO satellites, one of the dynamical phenomena is one-to-one orbital resonance. This figure 2 shows 2-dimension phase plans of these IGO satellites. This horizontal line marked L defined like this, and theta G is Greenwich mean time, and vertical line defined like this, delta A defined like this. Currently, all these 5 IGSO satellites are all in liberation status around L1. That's 75 degrees east. This table 2 shows theoretical analysis, theoretical values from our analysis. This column gives amplitude of semi-medial axis, delta A. For IGS 1, 2, 3, it can be reached 20 kilometers, and for IGS 4 and 5, it can reach 10 kilometers. And this column shows a period of A. It's around 3 years. This column shows the variation region of inclinations, and this is the period of our eye. It's from 78 to 100 years. From this column, we can see the orbit inclinations can meet the inclination resonance conditions, and the inclination resonance may occur, which often significantly affect the orbit eccentricity. Now let's move on numerical results. This slide shows how we did numericals. We use computer integrate its 12th order Adams-Fourier convention method. And the dynamical models includes EGM 28 Earth gravity up to 20-degree order. And of course, lunar solar perturbations and solar radiation pressure, including eclipse. And we use the normal air to mass ratio is about 1% kilometer per square meters. And the integration step is 13 seconds. Actually, it's too small, but in these cases, the eccentricity will be goes to very large, so we select 30 seconds for integration step. The total time span for integration is 600 years. This figure shows evolution of severe major axis. Just for clarity, we did two plots. The left one is for IGS 1, 3, 4, and the right one is for 2 and 5. It looks like a mess, but actually it's periodical and very regular. You can see if we use time spans just for 10 years, it's a little bit better. This figure 4 shows phase plans obtained by numerical results. It's just first 15 years. For comparison, we put theoretical results here. It looks like pretty much similar. This figure 5 shows evolution of orbit inclination. Again, we put two figures here. From this figure, we can see the variation regions of the orbit inclination are consistent with the results obtained from theoretical results, especially while the orbit eccentricities remain small in the beginning of the integration time. This figure 6 shows the long-term evolution of orbit eccentricity. From these figures, we can see, unlike the conventional geosatellites with low orbit inclination, the eccentricities of these ideal satellites will not always remain small after very long evolution and can reach to higher values. You can see it can reach the over 0.8. And we also can see within the first several decades, the initial near circle characteristics maintains unchanged. For long-term numerical integrations, a big issue is to check the results deliverabilities. This time we did this work using a totally independent method. We call it a simple analytic method to verify and assess the numerical results. This figure 7 just gives an example the difference between these two methods. From this figure 7, there we can see there are two curves on this figure that from two different methods, one from semi-analytical method and another from numerical method. We just talked before. It looks like they do not overlap exactly, but they do agree. They do agree each other very well. So we can see the results obtained by semi-analytical method are qualitatively consistent with the numerical results. Also, we did analysis of uncertainties. First one, we change error to mass ratio into half and double of the nominal value respectively. The similar results can be observed. We don't show the results here. You can see the results of long-term evolution are insensitive to normal error to mass value. Following IAD's mitigation guidelines, we did this uncertainty analysis. We increased and decreased in initial orbital altitude about 300 kilometers. We can see the eccentricities can also increase to higher values in long-term evolution. The increase or decrease in orbit altitude does not affect the long-term evolution too much. This figure 8 gives evolution of eccentricity with different senior major axes. One is for orbit, for initial orbit altitude, it's plus 300 kilometers. One is for 300 kilometer low. Again, these two curves do not overlap, but agree each other very well. So now let's try to answer the second question of possible mitigation strategies. Due to large variation of orbit eccentricity, IAD's recommendation for conventional geo satellite is not feasible anymore for these IGSO satellites. However, the large variation of orbital eccentricities remind us we will utilize these characteristics to reduce orbit lifetime of these ideal satellites after end of mission. This figure 9 shows evolution of eccentricities versus different initial longitude of a city node. We set a city node 0, 30, 120, and 225. So you can see totally different evolution pictures. From this figure, we can see for a certain initial longitude of city nodes, I select red one is the blue one is 120. The eccentricity of the ideal satellite can reach to a very high, to higher value rapidly. It's less than 100 years. And at this time, its orbit lifetime is significantly reduced. This figure 10 shows the relation between maximal orbit eccentricities after a longer evolution and initial longitude of acidic nodes. We can see in some window of acidic nodes, like for example from 90 to 180 and 210 to 150 degrees in this acidic node window. The maximal eccentricity of the ideal satellite can reach up over 0.83. That corresponding minimal altitude is lower than 200 kilometers. And at this time, the decaying with earthquakes. So that remains us, we can choose an appropriate launch time of these ideal satellites to reduce its orbit lifetime significantly. That's our answer. Okay. So this is a summary of our research. Characteristics of the one-to-one orbit resonance and orbit line variation still maintained in ideal satellites, especially while the orbit eccentricity remains small for several decades. And unlike conventional GEO satellites with low inclination, the eccentricities of these ideal satellites will not always remain small after long-term evolution, and they can reach to very high values. It's possibly because of inclination resonance. And the larger variation of orbit eccentricity make the recommendation of proposed by IDC for conventional GEO is not feasible for disposal of these ideal satellites after the end of mission. And a possible mitigation strategy of reduced orbit lifetime of ideal satellite is proposed by choosing appropriate launch time. That's all my talk. Thank you for your attention.